way because it gives some barrier protection even by the aluminum, and we have some cathodic or galvanizing protection or sacrificial protection from zinc. So it has a very good corrosion resistance, especially in the applications of construction and building. And as we know, in galvanizing, we use aluminum to create an alloy layer, an intermetallic that protects or prevents from zinc to get into a very exothermic reaction with the substrate. So something very similar happens in Galvalume when we add silicon. Thanks to the silicon, we can control the alloy layer formation so it doesn't get too exothermic, and you control the growth of this alloy layer. Depending on the amount of silicon content, we can control the alloy layer intermetallic formation phases that are present. We can found some intermetallic formations which promote the generation of small spandrel sizes or bigger or real spandrel sizes, and all the kinetic formations in the coating. So the silicon content is very, very important for us to control because then all the overlay is governed by the alloy layer formation. Another thing very interesting for us is just to understand the huge impact that we have from upstream lines, from the cleaning section, the presence of iron filings or plate out, and how it has a huge impact in the surface defects and the coating formation. There's a lot of information not given by myself, but by some huge people in the industry, like Mr. Daniel Liu, who has demonstrated the impact of the iron carboxylate presence in the substrate and how it tends to change all the whole kinetics in the coating formation. For example, when we have some iron soaps in the substrate or the iron carboxylate formation, the iron that is present in the substrate cannot oversaturate in the melt, so that changes all the kinetics in the alloy layer formation. So that's very important. We know that the presence of certain contaminants can change the kinetics in the Galvalume coating. So that's only a preface of what we are dealing. And as I told you before, in cold weather session, we have perturbance or a change in how the cooling or the cooling rate is happening in the strip. So that's only to take into account. In this galvanizing line is galvanizing line number 3 in Juventud facility. We don't have a cold rolling mill in the facility, so we receive strips from different cold rolling suppliers, all from Ternium. We received from 4 different cold rolling mills, reversible mills, 1 tandem line, and 1 PLTCM. So there's a difference there. And sometimes, in terms of the requirements, we can receive steel from other external suppliers. So we deal with different roughnesses, we deal with different amount of contaminants in the surface, and we need to have a very robust cleaning section to deal with the different characteristics of the strips that are incoming. So for the characterization of the molding defect in our coating line, in galvanizing line number 3 in Juventud facility, we are doing a general perspective in the cold roll steel origin. As I told you before, it's very different one from each other. We also quantify the amount of silicon present in the pre-melt pot and in the main pot. For our control of our process, we take the chemical control of the bath, both in the pre-melt and in the main pot, once every 8 hours, once every shift, just to take into account how we're dealing with everything. Also, we made a characterization of the melt in SEM just to understand the morphology of the silicon. We understand and we know that depending on the morphology of the silicon, it can behave differently. If we have an enrichment of the silicon phase, it can behave different. So that's only to take into account. And we also do a microstructural characterization of the thickness both of the alloy layer and the overlay. And also we did some surface characterization in the incoming strip. So as I told you before, there's a huge impact on the way that the strip is incoming for the consequence of the coating layer. So these are some general data of how the galvanizing line has the incoming strip. Just to give you a perspective, around 50% of our coils come from reversible mills, and around 50% come from tandem and PLTCM. So it's very balanced. But when we think about the mold-clean defect apparition, almost, and this is very interesting for us, the mold-clean defect appeared in 83% of the cases when the strip was incoming from a reversible mill. So that's very, very interesting. We have 50 and 50% of the distribution, but the mottling appeared in 83% of the cases when reversible mills were being processed. And another huge and interesting factor is that in approximately 95% of the cases, we were processing big coating weight coatings, like AC55, just to give you a general perspective of the phenomena that occurs in the operation of the defect. So what we observed is very, very interesting. So as you know, in the reversible mill process, there is a tendency of the accumulation of some contaminants, of some played out contents, some high presence of iron fines, of some thermal stains, carry-on passage of the oil emulsion. So we made a characterization of the strip before the entry section, just as it was, from a strip that generated the mold-clean defect. So we wanted to know how it was just before the start of the process. And we found, of course, we are aware that SEM is not the right tool just to make a proper characterization in terms of the carbon content, but only as a qualitative perspective or reference, we wanted to know how it all was working out. We have a pending process of doing some LECO and GDOs analysis just to have a better characterization. But we wanted to know what we found in the strip that appeared or generated mold-clean. So we saw high presence of carbon, and this was the appearance, the physical appearance of the strip just before the cleaning section. A quick disclosure: we don't have any electrolytic bath control in our line, just to give you a perspective. And when doing characterization in a strip that didn't generate the problem, we saw something like that. We didn't detect any other presence of alloy elements or contaminants. So that only I will like to take this with a pinch of salt, just to consider that it's only a reference. It's not. I don't want for you to think that these readings are precise, because SEM is not the right characterization technique for this to be understood, just only as a reference. As I told you before, we made a characterization of the silicon morphology in the melt, both in the pre-melt and in the main pot. And one of the wonderful and magnificent things that we have in Ternium is that we have more than one galvanum line. So we took samples from different galvanum lines just to see how we were as a benchmark, as an internal benchmark. I think we didn't notice anything weird or some enrichment in the silicon phase. So we didn't think or thought that there was a particular problem. We know as a general phenomenon, silicon is very important or very related to the modeling defect. If we have high content of silicon, it's more likely for it to appear, but we didn't see anything weird in the pre-melt or in the main pot, nor in the content of silicon of the silicon weight in weight percent in the main bath in the main pot. So that for us was very important. And just to share the nature of the defect, we have the molding appearance in one strip, the welding passes by with other supplier, and the molding defect disappeared just as magic. So it was very difficult to understand, because if it's something related to your bath, then it will appear in every single coil. But if it stops magically whenever the welding passes by, something weird is going on. So maybe you have to consider the characteristics of the strip, because that's the only difference that you can take into account. Of course, then again, as a reinforcement of the information, we know the importance of the silicon content in the operation of the defect, but the defect appeared in one strip, the welding passed by, and then it disappeared. So it worked like a magic trick or something, not a magic trick. So what we done, how we approach the defects. So mainly we changed the way that we fed the ingots in the pre-melt and in the main pot. We wanted to control the peak in weight percent of silicon, just to avoid a moment in which we had high silicon content in our pre-melt or in our main pot. So we changed the ingot addition process, and if you can see it in a graphic perspective, we can see first in the top left side, we see some peak contents of silicon, high peak contents of silicon, and those peak contents of silicon were related to molding events in our strip. And in weight percent, we didn't change a lot with changing the addition process or the ingot addition steps. What we controlled was the difference between peaks and low values. So we maintain some stable weight percent content in about 1.5, 1.4%. So that we changed. We saw better performance. We also made a characterization, and for me this is, if I have good 5 minutes to explain this, whenever we saw a good strip without mottling, next or very close to the alloy layer, we saw relatively high content on silicon, and that is easy to explain because in the solidification process it is common to see, if we think this as an equilibrium state solidification process at about 560 Celsius, the alpha aluminum dendritic phase are formed in between 520 and 480. The aluminum silicon binary eutectic is being solidified, so that's where in that range of temperatures, that's where the silicon is being solidified in the interdendritic region of the aluminum. So the aluminum is the first phase to solidify, and then the silicon is being solidified in the interdendritic region, and finally the last phase to solidify within the interdendritic region is the zinc. So in this general perspective, the silicon is expected to be found within the interdendritic region, and being found also close to the substrate and alloy layer, and from that way up till the surface of the coating. So when we didn't saw any mottling, we saw that behavior precisely. And whenever we saw mottling appearance, we saw silicon content near the surface of the overlay. So something happened that the silicon wasn't found mainly in the interdendritic region of aluminum, but it was found in the contours. It solidified in a flake way, and you can see it very clearly in the next slide. Right here we see silicon content near the surface of the overlay, so something went off that wasn't found in the interdendritic region, but mainly in the surface in another way that the solidification process happened. We also saw some differences in the spangle size. As we know, the strip contaminants have a huge impact in the size and shape of the spangle. And as a general conclusion, because we have a lot of work going ahead of us, we noticed that by slowing down in the after pot cooling section in one of the zones, if we turn it a little bit off, we turn to an equilibrium state solidification. And in that moment, we give silicon enough time to diffuse into the interdendritic region, so the silicon didn't appear in the surface of the overlay. Another way to control it and to make a better performance was by controlling the peak contents of the silicon. And for us, we have huge steps coming forward in terms of characterization and some other trials to make, because the winter session is coming and we want to be better prepared for this year winter in terms of the molding operation. So that for me concludes my presentation. I want to thank you.